Now we'll see some problem based on this concept, that is combination of lens. And if you see all these problems, I have taken the problems from the various sources, from JEE or as well as from NEET, and from various competitive examinations as well as from textbooks. So if you solve all these problems, you will get a good idea about combination of lens. So I will solve these problems. I just request you that whenever you see such kinds of problem, then first try by yourself. Whenever you see my video, then first you just try to solve the problem by yourself. If you are unable to solve it, then you just go for the solution. So first problem, basically I have divided the problem into two parts, level 1 and level 2. Level 1 are a bit easy problem and level 2 are tricky problem. So we will see first level 1 problem. First problem I picked from AIIMS 2017. A diverging lens with magnitude of focal length 25 cm is placed at a distance of 15 cm from the converging lens of magnitude of focal length 20 cm. So this problem says that there are two lenses. One is diverging lens, and the focal length of that lens, that is, this is our diverging lens, and the focal length of this lens is 25 centimeter. So we write f is equal to minus 25 centimeter, and it is placed at 15 centimeter from a converging lens of magnitude of focal length 20 centimeter. So here we have one converging lens, and the magnitude of focal length is equal to 20 centimeter. So we write f1 is equal to minus 25 and f2 is equal to 20 centimeter. Now a parallel beam of light ray falls on the diverging lens. So basically a parallel beam of light ray falls on this. Then you have to find the final image formed by this. So we will solve this problem into two ways. First, by just our traditional approach, that when the light ray falls on the first lens, then the image formed by first lens will serve as an object for the second lens, and then what will be the image formed by the second lens. Or we will also see the alternate solution, that when we replace this combination with equivalent lens by using the formula we just learned, then what will be our approach. So suppose that as this is a parallel beam of light, so it will diverge the light ray at its focal point, or it will form the image at its focal point, and that image will be virtual image. So as this lens is diverging lens, so it will diverge the light ray and it will form its image at the focal point, and this is its focal point f1. This is the value of f1 equal to 25 centimeter. So clearly it will form a virtual image at this point. So if we call this image as I1, then I1 is the virtual image, and this I1 will serve as a virtual object for this second lens. So now if you see that for the second lens, this is our object distance. So for second lens, the object distance is OD is equal to 15 plus 25, that is 40 centimeter. So we write that for second lens, which is our converging lens, u is equal to minus 40 centimeter, f is equal to plus 20. We have to calculate v. So we just apply formula 1 by v is equal to 1 by v minus 1 by u is equal to 1 by f. This is our lens equation. And we just apply this equation, then we get 1 by v minus 40 is equal to 1 by 20, that is 1 by v plus 1 by 40 is equal to 1 by 20, and from there we get 1 by v is equal to 1 by 20 minus 1 by 40, that is 1 by 40. So clearly v is equal to 40 centimeter. So the final image will be formed at the 40 centimeter from this convex lens. So suppose the image is formed at this point, we call it I, then I is equal to 40 centimeter from the convex lens. So and the image formed will be real, as the light ray will be finally meeting at this point I, and this convex lens converges the light ray, and the light ray will meet at the point denoted by I. So the image formed by this system will be real, and at a distance 40 centimeter from the convergent lens. Now, if we solve this problem by taking a combination of lens or the concept of combination of lens, then what will be our approach? So I will just show you. At first, we have to calculate the equivalent focal length of system. So what will be the equivalent focal length of system? And for this, we apply the formula 1 by f equivalent is equal to 1 by f1 plus 1 by f2 minus d divided by f1 f2. So clearly 1 by f equivalent is equal to 1 by f1. F1 comes with a negative sign, so 1 by minus 25 plus f2 comes with positive sign minus d is 15. 15 divided by f1 minus 25 into 20. So it's a minus 1 by 25 plus 1 by 20 plus 15 by 25 into 20. So we get 1 by f equivalent is equal to 1 by 20 minus 1 by 25 plus 3 by 100. So you just take LCM. You get f equivalent is equal to 25. So the equivalent focal length will be 25. We have to calculate then what is the distance of this equivalent focal length. So I have already shown you that the distance will be taken from the second lens. This is the place where equivalent lens will be placed. Then, and if delta is the distance of this lens from this lens, second lens L2, then delta is equal to D into F equivalent by F1. So it is delta is equal to 15 into F equivalent is 25 and F1 is minus 25. So we get delta is equal to minus 15. So the placing of this second lens will be from minus 15 centimeter from the second lens. That is, we have to place this lens, that is equivalent lens, at this point, and this distance is 15 centimeter. Now a parallel beam of light ray will come and they will meet the principal axis at the point equal to equivalent focal length. So 25 centimeter will, so from the equivalent lens, it will, the image will be formed at the 25 centimeter from this optical center. So clearly the distance at which image will be formed from the second lens will be 15 plus 25 centimeter, that is 40 centimeter. So at 40 centimeter from second lens, the image will be formed as the parallel beam of light ray will converge at that point, and as the light ray are actually meeting at that point, so we have one real image. And what will be the position of equivalent lens? Then the equivalent lens will be placed at a distance 15 centimeter from the second lens towards right side. So again we will see one more problem to make this concept more clear. Let us consider the case in which two convex lenses having focal length 15 centimeter and 10 centimeter are placed at a distance equal to 10 centimeter between them. Find the position and focal length of equivalent lens. And you also have to prove that a parallel beam of light ray will form the image at the same location in both cases if we go by our traditional approach and if we go by this formula method. So suppose we just solve this problem by, this is our traditional approach, that when the image formed by first lens will serve as the object for second lens, and the two are placed at a distance from, these two are placed at a distance between them is 10 centimeter. The focal length of first lens is 15 centimeter. Focal length of second lens will be 10 centimeter. Now when parallel beam of light ray fall on the first lens L1, so this is our first lens L1 and parallel beam of light ray fall on this, then it will form its image on its focal length, and its focal length is here, it's a 15 centimeter from this. So it will form the image at this point. Again, this light ray has already been intercepted by the second lens L2. So the image formation at this point, we call it I1, is a virtual image. And this virtual image will serve as a virtual object for the second lens L2, and due to which the second lens will refract this light ray and form a final image at a point denoted by I. So clearly the image is formed at the point I. Now we will apply the lens formula and then see that what is the value of this I, what is the distance of image formation from this lens, that is from this lens L2. So first we will apply the, for lens L2, U is the object distance, and as the direction of incident light ray is taken to be positive, so this direction will be positive, and the object distance for this is, suppose this is the optical center C2, so it is equal to C2I1, and the value of C2I1 is 5 centimeter. It will come with a positive sign. Again, the focal length F2 is equal to 10 centimeter, so we will apply the formula 1 by V minus 1 by U is equal to 1 by F, and 1 by V minus 1 by U comes with positive sign, so plus 5 is equal to 1 by 10. So if we solve it, then we get 1 by V is equal to 1 by 10 plus 1 by 5, that is 2 plus 1 divided by 10, and it is equal to 3 by 10. So V is equal to C2I is equal to 10 by 3. This is the position of the final image. Now we will calculate, or we will replace this whole system of two lenses by one equivalent lens. Then we will calculate the focal length of equivalent lens as well as the position of that equivalent lens, and we will see that the final image is formed by that equivalent lens at the same point I. So for equivalent lens, first we will calculate the equivalent focal length. So F equivalent is equal to, in fact 1 by F equivalent is equal to 1 by F1 plus 1 by F2 minus D divided by F1 F2. Both F1 and F2 comes with a positive sign. So 1 by plus 15 plus 1 by plus 10 minus D is 10, and F1 F2 is equal to 15 into 10. So from there we get 1 by 10 plus 1 by 15 minus 1 by 15. So we get 1 by 10, and F equivalent is equal to 10 centimeter. So focal length of equivalent lens is 10 centimeter. Suppose this lens, equivalent lens is placed at this point, we call it L equivalent. We call this lens as L equivalent. Suppose this is our L equivalent, then focal length of this lens is equal to 10. Now we have to second calculate the distance of this equivalent lens from the L2. So suppose this is delta, then delta, as we have already learned, is equal to D into F equivalent by F1. So D is 10, F equivalent is 10, and F1 is equal to 15. So we get 20 by 3. So this distance delta is equal to 20 by 3. Now the parallel beam of light ray will strike this lens directly, then they will form the image. At some point we will calculate the distance, image distance from optical center of equivalent lens. So as we know that for a parallel beam of light ray, the image is formed at the focal point. So V is equal to F equivalent, and it is equal to 10 centimeter. So the final image will be formed at a distance equal to 10 centimeter. Now we will see, if we prove that n is equal to delta plus C2I, then it means the image is formed at the same point. So we will calculate first delta plus C2I. Delta is equal to 20 by 3, and C2I is equal to 10 by 3. So if you add it, then it's 30 by 3, and it is equal to 10. So clearly the image formed by this equivalent lens is at its focal point and it will form the image at the same location. So in both way we can solve the problem. So if you have to calculate the equivalent lens, then you just apply the formula along with the consideration of sign, and then you also need to calculate the position of equivalent lens from the second lens. Now we'll move to next problem. And next problem I have picked from NEET 2015. Two identical thin plano-convex glass lenses having refractive index 1.5, each having radius of curvature 20 cm, are placed with their convex surfaces in contact with at the center. The intervening space is filled with while of refractive index 1.7. The focal length of this combination is. So in fact, this is a good problem. If you see here, so we have basically two plano-convex lens. So this is the first plano-convex lens. We call it L1, and this is second plano-convex lens. We call it L2, and the intervening space between them is filled with while of refractive index 1.7. So you have to calculate the focal length of combination. So if you see here, then we have basically three lenses. First is L1, second is L2, and third is the combination, or the we can consider the intervening space. So we consider this intervening space also as a oil lens. So this is oil lens and we call it L3. So basically we have three lenses, L1, L2 and L3, and we will just calculate the focal length of individual lens and then we just add it. So by using this formula, 1 by F equivalent is equal to 1 by F1 plus 1 by F2 plus 1 by F3. So for L1, the focal length is mu z minus 1 by R1 minus 1 by R2. So for this lens, if the direction of incident light ray, then this direction is taken as positive and the opposite direction will be taken as negative. And for first surface, for lens L1, first surface having radius infinity and the second surface have radius equal to 20 centimeter with negative sign. So it's equal to 3 by 2 minus 1 by infinity minus 20. So we get 1 by 2 into 1 by 20, that is 1 by 40. So we get 1 by F1 is equal to 1 by 40. So this is our equation 1. Now if you see here, for lens L2, we again calculate in this way, mu g minus 1 by R1 minus 1 by R2. If you see this lens L2, then clearly for this R1 is equal to plus 20 centimeter and R2 equal to infinity. So from there we get 3 by 2 minus 1 into 1 by 20 minus 1 by infinity, that is equal to 1 by 40, and it is equal to 1 by F2. Now for oil lens, that is L3, so this is a diverging lens and we have to calculate. So mu L minus 1 by R1 minus 1 by R2. Now if you consider this oil lens, then radius R1 comes with negative sign and radius R2 comes with positive sign. So this R1 comes with negative sign and this comes with positive sign, both having the value equal to 20. So this value is equal to plus 20 and that is minus 20. So from there we get mu L is 1.7. So 1.7 minus 1 into 1 by minus 20 minus 1 by 20, that is equal to 0.7 into minus 2 by 20, that is minus 2 into 7 divided by 20 into 10. So from there we get it's equal to minus 7 by 100. So 1 by F equivalent is equal to 1 by F1 plus 1 by F2 plus 1 by F3. So 1 by F1 is equal to 1 by 40. 1 by F2 is equal to 1 by 40. So basically it is 2 by 40 minus 7 by 100. So 1 by F equivalent is equal to 10 minus 14 divided by 200, it is minus 4 by 200, and it is equal to minus 1 by 50. So the equivalent focal length is equal to minus 50 centimeter. The negative sign signifies that it's a diverging lens. So basically this combination will behave as a diverging lens, and if you have to calculate the power of the system, then power is equal to 1 by f, and it is equal to 1 by minus 0.5. So the power comes equal to minus 2 diopter. So in this way we can calculate the focal length of this combination. If you see the option, then option second is correct. That is, focal length of combination is minus 50 centimeter. Now the next problem is from NEET 2016, and it is very similar to the problem we have already discussed. If you see here, it's a two equiconvex lens, and in the intervening space we just place water. So basically we have a system of two convex lens and a water concave lens between these two. So you just calculate the focal length of individual lenses and apply the formula 1 by f equivalent is equal to 1 by f1 plus 1 by f2 plus 1 by f3. Then you can calculate in that way the focal length of combination. So if you solve it, then you see the option 2 comes as true, that the focal length of combination is 3f by 4. Now the next problem is from JEE Mains 2012. A biconvex lens is formed with two thin plano-convex lenses as shown in the figure below. The refractive index of first lens is 1.5 and that of second lens is 1.2. Both the curved surfaces are of same radius of curvature, r is equal to 14 centimeter. For the biconvex lens, for an object distance equal to 40 centimeter, what is the image distance? So clearly you have to calculate for object distance 40 centimeter, what will be the image distance. For this you need focal length of this lens system, and this lens system is composed of two plano-convex lenses. So clearly these two plano-convex lenses are in combination of each other or in a contact of each other, and these two are thin lenses. So first we will calculate f1 and f2. So 1 by f1 is equal to mu1 minus 1 by r1 minus 1 by r2, where 1 by f1 where f1 is the focal length of lens 1, and we call this first plano-convex lens as lens L1, the second plano-convex lens as lens L2. So mu1 is the refractive index of lens L1, and 1 by R1 is the radius of curvature of this lens R1, and R2 is infinity. So clearly if I just draw the figure also, so this is our first lens L1 having refractive index 1 by 5. This is the radius of curvature R1, and the value is equal to 14. This is infinity. So 1 by f1 is equal to 1.5 minus 1 into 1 by 14 minus 1 by infinity. So from there we get it's equal to 1 by 2 into 1 by 14, that is 1 by 28. So this is the value of 1 by f1. Now we will calculate the value of 1 by f2. So this is our lens L2, and here R1 is equal to infinity and R2 is equal to minus 14. So 1 by f2 is equal to mu2 minus 1 by r1 minus 1 by r2. Mu2 is the refractive index of second plano-convex lens L2, and it is equal to 1.2. So 1.2 minus 1, that is 0.2 into 1 by infinity minus 1 by minus 14. So from there we get 2 by 10 into 1 by 14. So it's 1 by 70. So basically 1 by f1 is equal to 1 by 28 and 1 by f2 is equal to 1 by 70. Now these two lenses are placed in contact with each other. So 1 by f equivalent is equal to 1 by f1 plus 1 by f2, and it is equal to 1 by 28 plus 1 by 70. So if we take LCM of it, then it's 145 5 plus 2, that is 7 by 140, and 1 by F equivalent is equal to 1 by 20. So clearly F equivalent is equal to 20. And again F equivalent comes with a positive sign, so clearly this system behave as a convex lens, and it is also quite evident from this figure. Now for U is equal to minus 40, F is equal to plus 20, we have to calculate V. So we just apply length formula, 1 by V minus 1 by U is equal to 1 by F, and 1 by V minus U is equal to minus 40, 1 by F. So from there we get 1 by V is equal to 1 by 20 minus 1 by 40. So 40 and 2 minus 1, that is 1 by 40. So V is equal to 40 centimeter. So clearly the image distance will be 40 centimeter. If you see the option, then option B is correct. Image distance is equal to 40 centimeter. Now we will move to next problem. And this problem I have picked from AIPMT 2013. A plano-convex lens fits exactly into a plano-concave lens. Their plane surfaces are parallel to each other. If lenses are made of different materials of refractive indices mu1 and mu2, and r is the radius of curvature of curved surface of the lens, then the focal length of combination is. So as this lens, the plano-convex lens exactly fit into plano-concave lens, so the radius of curvature of this plano-convex lens and plano-concave lens are same. So this lens L1 is plano-convex lens, this lens L2 is plano-concave lens. Now I have shown here that if I put this plano-convex lens into plano-concave lens, then it exactly fits. So again it's given here that the diffractive index of first lens, that is L1, is mu1, while the refractive index of lens L2 is mu2. So we will solve it. So what will be our approach? We have to calculate the focal length of combination. So we will calculate the individual focal length by using lens maker's formula. So 1 by f1 is equal to mu1 minus 1, 1 by r1 minus 1 by r2. So for lens L1, R1 is equal to infinity and R2 is equal to minus R. So we just use these values. So mu L is equal to mu1 minus 1. So we get 1 by F1 is equal to mu1 minus 1 divided by R. Now consider the second concave lens. Second lens, that is concave lens, and 1 by f2 is equal to mu2 minus 1, 1 by r1 minus 1 by r2. For the second lens, r1 is equal to minus r and r2 is infinity. So it's mu2 minus 1 minus 1 by r minus 1 by infinity. So from there we get mu2 minus 1 divided by minus r. So the focal length of combination 1 by f equivalent is equal to 1 by f1 plus 1 by f2, and it is equal to mu1 minus 1 divided by r minus mu2 minus 1 divided by minus r. So it's mu1 minus mu2. So F equivalent is equal to R divided by mu1 minus mu2. So this is our answer, that the focal length of equivalent lens or the focal length of combination is equal to R divided by mu1 minus mu2. Now we will move to next problem, and this problem I have picked from AIIMS 2011. Two lenses of focal length minus 20 centimeter and plus 10 centimeter are put in combination. Find the power of this combination. So it's given here that P1 is equal to P1 you have to calculate. So F1 is equal to minus 20 centimeter. Clearly it's a concave lens. So P1 is equal to 1 by F1, that is 1 minus 1 by 20 centimeter. So it's we have to put in meter. So from there we get minus 100 by 20, and it is minus 5 diopter. As we have already learned that the power is equal to 1 by F in meter or 100 by F in centimeter. So P1 is equal to minus 5. Now we calculate the P2. So P2 is equal to 1 by F2, that is equal to 100 by 10, and it's equal to 10 diopter. So P2 is equal to plus 10. Now the lens having less focal length and or the higher power will dominate in the combination. Power of combination will be equal to P equivalent, or P is equal to P equivalent is equal to P1 plus P2, and it is equal to minus 5 plus 10, that is plus 5 diopter. So if you see the answer, then option C is correct. Suppose these two lenses are placed at a distance equal to let's say 10 centimeter. So suppose these two lenses are placed at a distance equal to 10 centimeter, then you have to calculate the power. Then what will be your approach? Then power P is equal to P1 plus P2 minus D P1 P2. So minus 5, sorry, plus minus 5 plus 10 minus D is 10 centimeter, so 0.1 meter into minus 5 plus 10. So we get minus 5 plus 10 minus 1 into minus 5. So we get minus 5 plus 10 plus 5, that is 10 diopter. So if we place these two lenses at a distance equal to 10 centimeter, then the power will be equal to 10 diopter. If we place these two lenses in contact, then we get power equal to 5 diopter. The problem is the combined power of two lenses in contact is plus 10 diopter. When they are separated by 20 centimeter, their power becomes 6.25 diopter. Find the power of individual lenses. So you have to calculate the power of individual lenses. Let the power of individual lenses be P1 and P2 respectively. So as per this problem, the combined power of two lenses in contact is plus 10 diopter. So when two lenses are placed in contact, then the combined power will simply the addition of their individual power. So P equivalent is equal to P1 plus P2 when they are placed in contact. And this is our equation 1, which says that P1 plus P2 is equal to 10. Now when these lenses are separated by a distance 20 centimeter, so separated by distance 0.2 meter, you have to very much clear that the distance must be in meter. So when they are separated by distance d is equal to 0.2 meter, we get P equivalent is equal to P1 plus P2 minus d P1 P2. So P equivalent is given as 6.25 diopter. So 6.25 is equal to P1 plus P2 is equal to 10. So 10 minus D, that is 0.2 into P1 P2. And from there we get 0.2 P1 P2 is equal to 10 minus 6.25, that is equal to 3.75. And P1 P2 is equal to 3.75 divided by 0.2, that is 375 divided by 2 into 10. So clearly we get it's 75 by 4. So from there we get P1 P2 is equal to 75 by 4. Now if you go by this option, then clearly as per this option P1 is correct. Option A is correct, where P1 is equal to 15 by 2 and P2 is equal to 5 by 2. So option A is correct. However, we will solve it and show that the value of P1 and P2 comes out to be 7.5 diopter and 2.5 diopter respectively. So we will calculate P1 minus P2. So P1 minus P2 square is P1 plus P2 square minus 4 P1 P2. So P1 plus P2 square is equal to 10 square minus 4 into 75 by 4, and from there we get P1 minus P2 is equal to plus 5 diopter. So we get two values, that P1 plus P2 is equal to 10 and P1 minus P2 is equal to 5. So this is our, if we consider this as our equation 2, then if we add 1 plus 2, then we get the value of P1, and value of P1 is equal to 15 by 2, that is 7.5 diopter, and value of P2 is equal to 1 minus 2, and it is equal to 5 by 2, that is 2.5 diopter. So option A is correct. P1 is equal to 7.5 diopter and P2 is equal to 2.5 diopter. So we will move to next problem. And this problem I have picked from JEE 2005. A thin concave and thin convex lens are in contact. Ratio of magnitude of power of two lenses is 2 by 3 and focal length of combination is 30 centimeter. Then you have to calculate the focal length of individual lenses. Now by seeing this problem, you may infer that you have placed two lenses in contact with each other, and you have to apply the formula of equivalent focal length of the combination. So clearly you have to apply the formula 1 by f equivalent is equal to 1 by f1 plus 1 by f2. Here the ratio of magnitude of power of two lenses are given. So the power of concave lens divided by power of convex lens is equal to, and the magnitude, the ratio of magnitude of these two lenses, the power of these two lenses is equal to 2 by 3. Again uh, you have to follow the order which is written in the problem, that is ratio of magnitude of power of two lenses, and in the problem first concave lens is written and then convex lens is written. So you have to take the ratio of power of concave lens and convex lens. So in this way you get f convex divided by f concave is equal to 2 by 3, and we may write that f concave is equal to 3 by 2 into f convex. So let f convex is equal to f, then f concave is equal to 3 by 2f, and again it's a concave lens, so its focal length will come with a negative sign. Now the formula of equivalent power length of this combination is equal to 1 by f equivalent is f convex plus 1 by f concave, and f convex is equal to f, so 1 by f plus, and f concave is minus 3f by 2, so 1 by minus 3f by 2. From there we get 1 by f plus 2 by minus 3f. Now if we take the LCM, then it's 3 minus 2, that is 1 by 3f. So clearly the equivalent focal length is equal to 3f, and if you see here, the equivalent focal length comes with a positive sign, that is the combination as a whole behaves as a convex lens. So the equivalent focal length is given as per this problem is 30 centimeter. So 3f is equal to 30 and we get f is equal to 10 centimeter. So clearly the focal length of convex lens is equal to 10 centimeter and focal length of concave lens is equal to minus 3 by 2 into 10, that is minus 15 centimeter. So if you see the option, then the focal length of individual lenses f concave is minus 15 centimeter, f convex is plus 10 centimeter, and option A is correct.